E-waste looks like trash, but it's ore, copper, gold, silver. And here's the danger. Drift the pH by a little, and your recovery tank becomes a toxic sludge factory. These lines run non-stop, inside chemistry windows that don't forgive mistakes. In 2022, the world generated about 62 million tons of e-waste. Most people think recycling is just shredding and sorting, but sorting only finds the metal. Chemistry actually recovers it. We're following 7 stages: intake and pre-sorting, shredding and liberation, magnetic, eddy current, and optical separation, hydrometallurgy, acid leaching, electro-recovery and electro-refining, copper, gold, silver, neutralization and pollution capture, and final metal output. And the hidden mechanism behind it all is 2 numbers, pH and redox potential. They decide whether you recover value or create pollution. 1 intake and pre-sorting. E-waste doesn't arrive neatly separated. It arrives as chaos, phones, boards, cables, chargers, plastics, sometimes with batteries still inside. This is where the first failure can happen, because 1 lithium battery in the wrong stream doesn't cause a problem later. It can ignite a shredder immediately. So intake works like triage. Batteries out first, pressurized parts out, toner and hazardous components out. Board-rich fractions separated early, thick copper cable separated early. If hazard sorting fails, the line stops, or it burns. The plant doesn't start with machines, it starts with control. 2. Shredding and liberation. Now it gets loud. The shredder isn't trying to make small pieces, it's trying to achieve liberation, freeing metal from plastic, fiberglass, and adhesives. Too coarse and copper stays bonded to plastic. Too fine and you create dust. Dust that can carry heavy metals. So plants use staged size reduction. First shred, break open. Second granulation, liberate, screening. Keep particle sizes inside a tight window. And it all runs enclosed, negative pressure, filtration, because nothing toxic is allowed to leave the building. If particle size drifts, you lose metal, or you create dangerous dust. 3. Magnetic/eddy-current/optical separation. Now the stream looks like confetti, but it's engineered confetti. Magnets pull out ferrous steel, fast and clean. Then eddy current systems throw non-ferrous metals into a different trajectory, especially aluminum. What's left goes through optical and sensor sorting. They detect differences humans can't: reflectivity, material signatures, contamination. This step doesn't recover gold yet. It does something more important. It concentrates the right feed so chemistry can recover metals economically. If sensor sorting drifts, you dilute the high-value stream, and you can lose an entire shift's margin in hours. Chemistry hates randomness. This step removes randomness. 4. Hydrometallurgy, acid leaching. Now we reach the part most people never see. Board-rich concentrates go into reactors, not to melt metals, to selectively dissolve them. And the entire game is controlled by 2 numbers: pH, how acidic the solution is, and redox potential, how aggressively it oxidizes metals. First, the principle: too low, and copper won't dissolve efficiently. Too high, and you start dissolving the wrong metals: iron, nickel, zinc. That turns copper solution into contamination soup. So real plants lock chemistry into rails: pH probes, ORP probes, dosing pumps, temperature control, agitation to eliminate dead zones. Controllers correct pH and redox every few seconds, faster than operators can react. If ORP overshoots, impurities follow the copper. And later, instead of smooth copper sheets, you plate rough, brittle, burnt deposits that have to be scrapped. By this point, the plant has already spent millions getting here. 1 control drift now doesn't slow production. It destroys the batch. The shredder makes pieces. The reactor makes purity. 5. Electro-recovery/electro-refining. Now value becomes visible. Once metals are dissolved, you pull them back out with electricity. For copper, this is the workhorse moment, electro-recovery. This is the moment value becomes visible. A sheet of copper grows, atom by atom. And 1 setting decides whether it plates clean or burns on the surface. Current density, tuned so copper deposits smoothly, instead of turning rough and brittle. If pH or impurities drift, cathodes plate garbage instead of copper. 6. Neutralization and pollution capture. After recovery, you're left with liquid streams that must be stabilized. This is where responsible plants separate themselves from backyard operations. Neutralization raises pH in a controlled way to precipitate dissolved metals into stable solids. Scrubbers capture acid mist. Filters capture fine particles. Water is treated before it leaves the site. If neutralization runs too fast or too far, the wrong compounds form and the loop breaks. Recovery without capture is contamination with paperwork. 7. Final output. At the end, nothing looks like trash. Copper leaves as cathode sheets or clean granules, refined feedstock for new products. And here's the payoff. This line can turn e-waste into metals at 99.9% purity. And the environmental return is real. Every ton recovered is less primary mining, less energy, and fewer toxic tailings. Every clean copper sheet leaving this plant means fewer mines blasted open, and fewer tailings dams sitting behind walls of waste. E-waste isn't trash, it's high-value ore. But only if you control the invisible corridor, pH and redox, minute by minute. What should we break down next? Comment batteries, rare earths, or boards, pick one.